This subassembly will plug onto this part of the repeater controller, which goes to the main 440 repeater. The module that will be plugged in here will be a ID generator and a audio delay. The audio delay uses a PT2399 IC. It is adjustable from 0 to several hundred milliseconds. And this is for muting DTMF tones and squelch tails. This is the chip for the delay. It's a PT2399. It does everything without too many external components. You can do sound delay or echo. The ID CW is generated by this C8051F370 IC. It has a D to A converter, which is right here. This chip generates the CW ID, an O and a K in CW for touch tone fidelity. So if you enter certain functions of the repeater controller, you'll get an OK in CW if the tones are decoded and are valid. There's a low pass filter here to filter out the staircase that is generated in the D to A converter. That's these two op amps here. Then there's a tone level out. This is brought back to the repeater controller. This is a summing amp. It brings in audio from the controller and inserts the CWIDer in the receive path from the repeater. The delay circuit is inserted here, buffered, and then sent back out to the repeater controller. So this originates from the repeater and this goes on to the controller, and this is the delay circuit here. So we have ID down here and delay circuit up here. Looking at the repeater controller, this aux port is where the ID and delay subassembly plugs on to the repeater controller. This is where the board will fit onto the repeater controller. It plugs into that header and screws down to that standoff. ST305 and 306 are removed. These are only here if there's no options or subassemblies plugged on. Also, from the original controller, had to add this TTCONF, which is touch tone confirm, which goes over to the micro over here, and that tells the micro to send a CW OK. Touch tone confirm is sent by two of the micros. It's an active low on the main repeater controller. If a valid touch tone is received, this will toggle low temporarily. Goes to the crossband interface IC. And I believe it also goes to the main controller, TTCONF. But that's some wire mods that had to be made on the board. Is touch tone config. Then ID key and ID trigger also had to be hand wired onto the bottom of the controller because all this came along later after I designed the main controller board. So we needed a couple extra pins here. These were spare pins brought out to test points. The touch tones are gathered on the repeater controller before the delay. So the touch tones are gathered right after this op amp here. This is the receive in of the repeater. And the touch tones are gathered before it comes into here to the delay circuit and then out to the main controller. The audio that goes to all the other controller interfaces. This is the PCB layout for the ID delay module. The size had to be 2 inches by 1.1 inches wide. So the entire circuitry had to fit on this size board. Had no problem fitting this entire circuit onto that board. These are the wire mods I had to make on the bottom of the board for the ID module. Had to put green wires on the bottom to make these connections. One is from the main micro, and I'll draw in where they go. Usually use vias to tie the wires together underneath the board. This is 36 gauge Teflon silver coated wire. And it connects the test points that were spare pins on the micro and connects it over to that header. So there's a few of these mods for the ID controller that I had to make on the bottom of the board. And once those were made, then we could get the IDER to function properly and get the DTMF confirm also to work via the code. So those mods are now made. Okay, we have the parts in and the boards. First we got to mount a surface mount part, the micro, which is very small. This is under do this under the 3D microscope. We use this Formula 951 Kester flux. It's much better than the standard flux. It's very, very thin. It doesn't leave a lot of residue behind. This is the standard flux there on the left, and you can see that the Kester is very, very thin. And when you're doing these small chips like this, it really helps getting the solder to stick to the chip and not from pin to pin and so on. So here's mounting the micro, and you just kind of bridge the solder across it. It does look like you're shorting it out, but as soon as you put that Kester on there, it just immediately soaks that solder right into the pin itself, and it just flows right across. And any excess, if you have too much, you can take solder wick and pop it right off, any extra solder. But if you notice it, as you go along the pins, it eventually sucks that solder right into the pin and into the printed circuit board, so you get a nice clean mount for this really small surface mount part. You can see here there's a little extra, but you can kind of work it through and maybe even add a little bit more flux if need be. But the real trick to this is the right flux. Yeah, here we add just a little bit more, and it'll just form the solder right into the printed circuit board and right into the chip, and there'll be no shorts anywhere, and it works out really well. This type of chip is kind of hard to mount because the solder has to flow up underneath it. This one is a little bit crooked, but it's still making good contact. Be nice if I could have got it a little bit straighter. They are hard to hold down. The J-lead package is much easier. Here's an example of a J-lead package. Using the same solder flux, you always want to use that same Kester solder flux. But soldering the pins of a J-lead are much easier than the LCC, which is what the micro we're using presently is. So anyway, here's back to the LCC. It's mounted, and we're ready to build the rest of the board. Now it's time to mount some of the surface mount parts, and we'll kind of show a couple of them here. That's what you call tombstoning. When it pops, one side pops up when you solder it. Normally there's glue underneath of them in production that holds them down. Here's an IC chip I'm going to mount. Probably an op amp. I think that's one of the op amps. And also you can see all the yellow on the sheet of paper there. That's the bill of material. I yellow the parts as I place them to look for errors in the bill of material. So we're going to solder on this SO14 package, which is the op amp for the IDER and delay board, building two boards at the same time. So I'll have two of them to work with, because I do have two repeater controllers, one just for testing purposes. So here we're cutting a header. This is the programming header for the micro. It's just a 4-pin single 2mm header. I buy them in 25 lengths of 25 positions, and then just cut them up. It's much cheaper that way. Once the boards are built, mostly built, you need to clean them, and that process involves distilled water and isopropyl alcohol. 91% is the best I can get right now. You want the highest percentage possible. So you just soak the boards in the alcohol, just totally saturate them, and take a toothbrush and brush off all the flux you possibly can. This most of the flux comes from the core of the solder itself. It's not the I don't use the liquid flux except for mounting those surface mount parts that are pretty dense or pretty small. Once you alcohol clean the boards and brush them good, you soak them in distilled water for a little while and shake them up good, and then you take a heat gun to them and you dry them as soon as possible. You want to get the water off of them, and that way it won't penetrate any parts. The last parts to mount are the potentiometers, the trimmers, and the headers and connectors. And the reason they're last is because we don't want the wash to get into them. So we put those on last. And then here's a few snapshots of the board under the 3D microscope, just to take a quick look at some of the connections. I've written some code in assembly language for the micro on the IDER circuit. These are the port equates here. ID key, repeater key during active code. So the repeater has to be keyed when the code is being outputted. ID trigger, this is from the main controller. It's basically a COR that comes in from the main controller. Makes the 440 repeater ID in the 10-minute increments from any input source via crossband or Echolink. Then we have a couple test points. Test point 1 is a 1 millisecond time base output. Test point 2 is a D to A sine wave generator duration pulse. So when the sine wave output starts, the bit goes high, and when the sine wave ends, it goes low. It's just a duration. And then TT config, one of the added green wires I did earlier on the motherboard for touch tone code confirmation. So when you hit a touch tone, you'll get an OK in CW. C detect is not used. ID key is used instead. So C detect is unused. Then we have options 1, 2, 3, and 4. Option 1 is a single tone select, basically just for testing. It just places a single tone out of the microcontroller. Option 2, CWID 60-second interval. It creates a faster time in between CWIDs of 60 seconds instead of 10 minutes, mainly for testing purposes. Slow code select, option 3, is another test strap, and it just slows the code way down for testing purposes. Then we have option 4, courtesy tone defeat. If you don't want a courtesy tone, you can put that option in, and it mutes the courtesy tone. LED output follows code output. TP3, which is unused at this time. And all those labels are here on the micro. And the programming pins are right here. 4 pins go to the programming pod for the micro. And the options are placed across this header, options 1 through 4. Data location assignments. The CBY1 through 10 is where the CWID resides. Show that here. of how this is done with the call here. The CW is in 10 bytes. It takes 10 bytes for the entire ID, or 80 bits. A space between letters is 00. A dot is a 1. A 0 is between, you got dot, 0, dash, which is 2 ones, then a 0, then another 2 ones. So you get dot, dash, dash, and then another 2 zeros, because that letter is finished. Now we do this number, 9. So you got 2 zeros to make the space between the two letters, or the number and the letter. 2 ones together create a dash, then a space, then 2 ones together create another dash, then a space, 2 ones again, and a space, and 2 ones again, a space, and then 1 is for the dot, for the number 9. Then 2 zeros to separate the number from the next letter, and on and on. So each letter is separated by 2 zeros. Every dot is a 1, every dash is 2 ones, and they're separated by 1 0. And this is all rotated out left. And this is where all these locations are here. Here we do the CW code rotation. This is what generates the code. You rotate left the accumulator and toggle M_code, and it's either a 1 or a 0 that's shifted. And as it shifts, it turns on and off the timer 2 interrupt. Once the timer 2 stops, the sine wave stops. Timer 2 activated, then the sine wave outputs on the D to A output pin. This is what this flag here does. And there are shown here to get the entire code through. There's 10 bytes. This takes 10 sets of 8 rotations, and this is all the way down to 10. Timer 2 generates the sine wave and tone frequency for the ID and the courtesy tone. I set the courtesy tone to 2,475 kilohertz for a Quindar tone, which was used back in the Apollo days for communications. And it's at, I believe, 250 milliseconds. That tone is the courtesy tone. The ID frequency is 1,375 hertz. As measured, I was shooting for 1,350, but I made it 1,375. These overflow timers are set for values which the timer will overflow to generate a sine wave at these frequencies. So that's timer 2. Timer 0 is used to generate the 1 millisecond time base for all the timers that I'm using in the micro. This loads the code shown here. That's where all of these locations, all 10 bytes, are loaded with the 8 necessary bits to get the CWID to line up. So when you load like the first letter of the ID, which is W, you see 001, 01101. That's the first 8. So that's what we have here in CBY1. And this is half of a dash, so the second half of the dash is started here. So this is bit 9, or the beginning of byte 2. And it goes on down the row until number 10 down here. And now some preliminary testing of the board here. There's the OK. The ID with courtesy tone. Okay, I have the ID/delay board placed on the repeater controller, and we're ready to try some tests out here. Okay, that's the ID here. Now we're going to test the CW OK for entering touch tones. Right now we're in option 2, crossband. Now we're going to enter option 4, echo link crossband receive only. Try to hold the camera here. And it took the code. And now we're in option 4, Echolink and crossband receive. I'll go to option 5. And it took it. And option 5, Echolink crossband full. So every time we add a code and the code is correct and decoded correctly, you'll get an OK. Now we'll test out the courtesy beep here. We key up. Green LED is as if the repeater is keyed. Once the repeater is unkeyed, get a courtesy beep. The CWID board seems to be functioning fine. Now testing the delay part of the circuit. Testing. 1, 2, 3, 4. Test. 1, 2, 3, 4. So there's the delay. And that's the delay IC part of the circuit. So it appears the circuit is functioning pretty well. And time to move on to the next subassembly.